This Bowman DA3 Fourier transform infrared spectrometer has a 2 milliwatt helium neon laser inside of it, and it is absolutely beautiful. But it's also the first proper real deal laser that I've ever had the opportunity to play around with, which is to say that I don't actually know a whole lot about lasers. And so before I ever put any power into this thing and got that laser lasing, I went on a bit of a journey to learn as much as I could about how a laser tube like that works, and to put the words 2 milliwatt helium neon into some form of context. And on that journey, I ended up picking up this thing. This is a Symbol Technologies LS7000 barcode reader from 1987. And inside of it is a 1 to 2 milliwatt helium neon laser tube that is almost identical to the laser that's in this infrared spectrometer. So I picked up this barcode scanner solely for the laser tube, and then I promptly nerd-sniped myself with trying to figure out how this thing works and how barcode scanners in general work. And actually, how do barcodes work? Like, what do all those vertical lines even mean? Interestingly, this is a problem that my brother is actually pretty intimately familiar with because he has a little shop up in Pittsburgh called Love It Sundries. And this is just 3 of the 100+ products that they make in-house. And if we take a look at the bottom of the mechanic soap box right here, we can see that this product has a custom barcode on the bottom of it. So if a customer comes in and wants to buy this mechanic soap, they can set it on the table and my brother, using his barcode reader, can read that barcode, pull up all the information about the specific product, and know what to charge the customer. But why a barcode? The history of the barcode is absolutely fascinating, and it spans back nearly 100 years. And whenever I'm trying to research something that I don't really know a whole lot about, one of my first sources is always Hackaday. Hackaday is one of my all-time favorite websites, and of course, there's an article on here all about the barcode and barcode scanners called The Eloquence of the Barcode. And it has a ton of wonderful information about the history and how to build a barcode up and how to actually read a barcode. And it was written by Adam. And Adam happens to be a friend of mine, so why don't we just ask him? Adam, thank you so much for taking my call. It's good to see you, man.
Hey, Dave. Nice to see you again. How are you doing?
Good, man. All right, so I know that you're a Hackaday writer, but why don't you tell the people like who you are and what you do?
Adam Fabio. I'm one of the editors over at Hackaday. So I do writing and I edit other people's stuff. Also, that's kind of my side gig. I've worked for a few different companies over the years, but a lot of my career has been around barcodes, which is why we're here. But I'm working for one of the big, larger companies that makes barcodes and barcode readers and handheld computers.
For somebody of my generation, it feels like barcodes have always been a part of our life, but really they just kind of showed up in the 70s, even though their history goes way back before then, right?
The real beginning for barcodes, though, was the 30s, where they were trying to sort punch cards. So 3 guys, John Caramo, Douglas Young, and Harry Sparks. They worked for Westinghouse. Those were the 3 guys that actually created the first 4-bar barcode, and it was for sorting cards.
A barcode reader from the 1930s seemed way too cool to just kind of let slip by like that, so I started doing some reading about it in the patent. Apparently Westinghouse would send out a bill, and on this bill was a detachable stub. You would tear this off, attach it to your check to pay for your power, and send that back to Westinghouse. They would send it through the machine, which would shine a light on that stub, and then they had individual photocell tubes that would pick up the reflected light coming off of it. And depending on which photocell tubes picked up light and which ones didn't, it would trigger certain relays that would route the checks to specific locations so that they could separate all the checks into the appropriate district. What a fascinating device that I had never heard of until this moment.
Basically, in the 1940s, the Bernard Silver and Joseph Woodland were the 2 guys that really kind of kicked things off. They started creating these new barcodes. The idea was to read something with a reflected light pattern. So light would go out, light would strike it, and light would reflect back, and they'd pick it up with a photomultiplier tube. You're trying to encode a serial data stream on a printed media. So what serial data streams did he have available? Morse code. Everybody had it. So he took Morse code, made bars out of it, and printed it. it turned out it wasn't quite so easy to read because there were a lot of easy ways to transpose and mistake one character for another. Morse code as a character set wouldn't work, and that's when they started delving into different sorts of encoding schemes and different ways of laying things out.
Silver and Woodland's prototype used something called a photomultiplier tube, much like this one that I've had hiding out on the shelf over there for years. These things are fascinating. They have a collection of diodes in there that can be excited by something as small as a single photon. And when they do get excited, they create secondary emission. So a photon coming in the front can strike the first diode, which will kick off a couple of electrons that'll strike the second one. That'll kick off a few more that strike the third one, and this will cascade all the way to the bottom until you get a nice big signal out of the other end. So maybe someday we'll figure out how to power this thing up and see if we can detect single photons with it. But Woodland's design was patented, and he tried to sell that patent to IBM while he was working there. And IBM showed initial interest, but ultimately didn't end up buying the patent. So instead, he sold it to Philco. Philco did nothing with it, so they sold it to RCA. You can see that things are getting a little messy, and they get even messier because so far we've talked about Kermode, Young, Sparks, Silver, and Woodland, but there were many more involved in trying to solve this problem of reading encoded data using reflected light.
A fellow named David Jarrett Collins was working on essentially tracking inventory and locations of train cars. You want to know where all those cars are, what they're loaded with, etc. He created a system of reflective vertical stripes called CarTrack, and he was working for GTE Sylvania at the time. That system actually took off and was used for quite a while, and this is in the 60s into the 70s. In fact, if you see train cars go by, there's still a few out there with those plates and the stickers on them. GTE ultimately didn't do a whole lot more with these, but he eventually left and started his own company called Computer Identics. One of the things the company focused on was decoding barcodes and reading them.
We're getting pretty close now. Computer Identics further evolved their design to change away from the reflective tape that's colored into black and white, and started using a helium neon laser to read that black and white code. That's sounding very familiar. But there was a lot of other people that were still playing with this. RCA still was working on it, and they were playing around with circular barcodes that looked like a bullseye. And so many others had thrown their hat in the ring by this time, which meant that it was absolute and utter chaos.
Someone needed to standardize this because the point of sale systems that they had, every company is completely proprietary. The National Association of Food Chains got involved, and they were the ones that ultimately made the decision. So you have to put this in a small space because no company wanted to give up precious space on their product that they'd use for marketing or ingredients or anything like that. It had to be printable, it had to be readable, and it had to be something that the supermarkets, the supermarket consortiums all agreed on as well.
Now, we're essentially just talking about the ability to read information off of a piece of paper, and the encoding of that information can kind of be arbitrary. It can be whatever you want it to be, and there are a ton of different encoding schemes out there. What we're going to focus on today is the UPC, which I think is a lot more limited. It can only encode numeric digits between 0 and 9. But the reason that we're going to focus on UPC is that this is the barcode that's on pretty much every retail product out there. If you look at my brother's mechanics soap here, on the bottom of it is the UPC barcode that we're going to take a look at today, but this is a little small for me to see, so I sent my brother an email and said, could you send me the original file for that barcode? And he did, and I was able to print it out, and it looks so silly to see a barcode printed out this huge. But this is going to make life a little bit easier for figuring out exactly what's going on. And really, a barcode has a cheat sheet on it. What is encoded in those vertical lines is written right along the bottom, 85962200613. That's it. There's nothing else in there except for a little bit of extra stuff so that way the reader knows what's going on. It starts on the very far edges. You have something called the quiet zone. This is an area of white space that has to be there so the reader knows that it's actually seeing a barcode. And then just inside of that, on both the end and beginning, you have a start bit and a stop bit. And this is actually 3 vertical lines that go dark, light, dark. And it's the identical vertical on both sides. And then right in the very middle is the middle bit. And it's actually composed of 5 vertical lines that go light, dark, light, dark, light. And then everything else that's encoded in here is just those 12 digits that we see along the bottom. But this is where things get a little tricky because the start and middle bit and end bit are all very skinny. But if we look at the actual digits that are encoded, some of the bars are skinny, some of the bars are fat. Like, this looks like chaos to me. So what on earth is going on here? Each digit is made up of just 4 bars of variable width. And I initially hated this. But as I understood it a little more, it started to make a little more sense. But first, let's take a look at, say, the digit 0 on this barcode right here. And we can see that we have 2 zeros on the right side of the middle bit here. And it's made up of a fat dark bar, a kind of fat light bar, a skinny dark bar, and a skinny light bar. And that's it. Those 4 bars right there represent the digit 0. And you can see that we have 2 zeros in a row, so we have the exact same thing duplicated right next to it. However, if that 0 is on the left side of the middle bit, the colors are now inverted. We start with a fat light bar, then a kind of fat dark bar, then a skinny light bar, and a skinny dark bar. But here's the kicker. I said that each digit is represented by 4 bars of variable width, and I hate this. I hate the concept of variable width. But if we break it down far enough, it's not variable width. Each digit is actually composed of 7 modules, and each module has a very defined size. So if we think of this in terms of binary, and we say that a light module is a 0 and a dark module is a 1, and we go back to our 0 digit and break this up into its individual modules, we end up with 3 dark modules, 2 light modules, 1 dark module, 1 light module. And 3 plus 2 plus 1 plus 1 equals 7. So since we now know that it's actually just 7 modules per digit and we can only represent 0 through 9, we should be able to go through this barcode one by one and completely match it up to the numbers on the bottom. But what do these numbers actually mean? 8 is the product classification, 59622 is going to be the manufacturer number, 00613 is going to be the product number, and 2 on the end is a check digit. Now, of course, it's a little more complicated than that because you have to buy UPC codes and there's only a limited number of them, and the whole thing is tied up with some governing body, I think called GS1 now, that's like tons of red tape and kind of expensive, but that's not the point of today's video. However, the check digit on the end I think is incredibly fascinating because this is a way of ensuring that you read back the barcode correctly. And you have a very specific math equation here to figure that out. And so you add together all of the odd positions and then multiply them by 3. So that's going to be 8 plus 9 plus 2 plus 0 plus 6 plus 3, which equals 28. 28 times 3 equals 84. And then we take all of the even positions and add that to the above results. So it's going to be 5 plus 6 plus 2 plus 0 plus 1, which equals 14. Then 84 plus 14 equals 98. Then we divide that number by 10 and take the remainder. So 98 divided by 10 is 9.8. And if the remainder is not 0, we subtract it from 10. So 10 minus 8 equals 2. And that's why our check digit on the very end here is equal to 2. So let's go left to right and read this out and totally break down this barcode. And so we have 101, this is the start bit. Then we have 0110111, this is 8. Then 0110001, this is 5. 0001011, this is 9. 0101111, this is 6. 0010011, this is 2. And then that is repeated again. Then we get to a 01010. This is our middle bit. And then from here on, everything is going to be the inverse of what we were just looking at. So starting with 0, we've got 1110010. This is again duplicated. Then we have 1010000. This is 6. Then we have 1100110. This is number 1. Then 1000010, this is 3, and finally 1101110, this is 2. And we finish it all off with a 101 that is our end bit, and another quiet zone on the other side. And there you go. Now you know how to read a UPC barcode. You should be able to look at the bottom of any retail product out there, like this Love It Sundries soap, and figure out exactly what those light and dark lines mean and how they match to the numbers below. But the human brain is a pretty capable computer, and we were reading barcodes in the 1970s. So how did we convince something like this to read this? This barcode scanner is branded a Telzon LS201, but it's actually built by Symbol Technologies, and it's an LS7002. The LS7000 was, I think, one of the very first handheld barcode scanners, and the design was spearheaded by one Edward Barkan, who was essentially the Steve Wozniak of Symbol Technologies. This man did amazing things with barcode scanners, and unfortunately he passed away very recently. But his legacy lives on in this ray gun here, which looks like it's straight out of a sci-fi movie. I absolutely adore the aesthetic on this thing, but there's a lot of really exciting stuff going on inside that dictated the shape. And so in order to see that, there's just 5 screws that we got to remove, and then the whole thing cracks right open. This thing is absolutely beautifully packaged. You can see that there's virtually no wasted space and everything is super compact. Right here in the handle we have a foil covered brick. This is going to be the high voltage generator that's generating, I don't know, maybe 10,000 volts or so for the helium neon laser tube that's inside of this big plastic casing right here. And looking at the little sticker on the side here, I think that's a 1.1 milliwatt helium neon laser, which is pretty impressive to stuff in something so small. There's a mirror here that reflects it up to another mirror over here that will be wobbling back and forth to create a wide scan line so that it can scan across the entire barcode. And then on the very top of this, we have all of the electronics with our photodiodes on the front here for detecting what the barcode is. So let's see if we can break this thing free from its plastic cage here and get all of the components out separate. First up, the trigger, which just slides right off a plastic peg. Then I'll pull the high voltage supply brick out and get it out of the way. After popping the trigger PCB loose, the whole thing is pretty much ready to be pulled out of the plastic case now. Easy peasy. Then I'll flip the main electronics PCB over and unplug the motor, and we're almost completely separated here. I'll unplug the high voltage power supply as well as the external plug and cord. Next, let's see if we can get the plastic casing off of the HeNe. I want to see that laser. After removing the foam, there's 2 little screws that go through the plastic at the front and 2 more screws that hold the optics in place in the back. I'll have to cut my HeNe power sticker here, but at least it'll be a clean cut. Then finally, the plastic just pops right off, giving us a glorious view of the HeNe. Finally, on the main electronics board, I'm going to carefully peel back all the RF shielding so I can get my eyes on the ICs underneath and maybe get an idea of just what is going on. For something so compact, that was surprisingly easy to get apart, and really, if we're looking at primary components, there's not that much. You have the laser, the high voltage generator, the moving mirror, and the control electronics. And that's it. At the very front of the control electronics here, we have 2 photodiodes that are heavily shielded, but they also each have their own little filter here that only allows helium neon laser light to pass through, and it blocks all other light. Looking at the main PCB here, I don't actually have schematics for this, but it's not explicitly necessary to kind of get a grasp of what's going on. We just got to look at the ICs. Right here we have an LF347. This is a quad operational amplifier. So there's 4 amplifiers inside of this IC. That comes over here to an NE5532. This is a dual low noise operational amplifier. Coming out of that, we have an LM393 right here, which is a dual comparator. So up to here, this is all pure analog electronics that's just amplifying low signals, squaring them off into proper square waves. Right here we have an LM555, the greatest integrated circuit of all time. This is just a simple little digital timer IC. And then all the way over here on the end we have a TL062. This is a dual operational amplifier. My guess is that this probably is the op amp for the beeper here that beeps whenever you get a scan. But as you can see, there's like practically no digital electronics anywhere on here. It is all purely analog. Sitting on top of the helium neon laser, we have this little electric motor right here that has a mirror bolted to it. So that mirror can rotate left to right very rapidly so that we can take our pinpoint of light from the laser and turn that into a line of light that is scanning left to right. And of course, we have the piece de resistance, the entire reason that I fell down this barcode rabbit hole in the first place, the uniphase helium neon gas laser. This is a real deal proper laser, and it is super cool to see this thing free from its plastic cage. Now, of course, I'm going to talk about how all of this junk on the table here is used to read barcodes, but like, there's a laser on the table, man. There is no way that I am going to be able to concentrate enough to continue filming unless I stop everything right now and talk about how cool helium neon lasers are. So buckle up, we're going on a tangent right now. Well, not right now, because before we talk about the helium neon laser, we need to talk about this little guy right here. This is a neon indicator bulb, and these are ubiquitous. They've been used for the last 70 years in all sorts of stuff, and they're still used in things today. There are effectively 2 electrodes in the middle of a little glass envelope that is filled with neon gas. Now, filled with neon gas is a bit of a misnomer. It does only have neon gas in there, but it's at an incredibly low pressure, much lower than atmospheric pressure. So what happens whenever you put a high voltage potential across these 2 electrodes? The electrons in the neon atoms get excited and they jump to a higher energy state. Now, when those atoms strike the cathode, they're brought back down to a low energy state. And when this happens, that change of energy states causes a photon to be emitted. And the photons that are emitted from neon gas are in that nice red-orange color. So you get a really beautiful glow out of these little neon indicators. But you can also see that on DC voltage here, all of the glow is centered around one electrode, because that's where all of those atoms are dropping down to a different state and emitting photons. So we use that same principle in a helium neon laser, only as the name would suggest, there's 2 gases inside of that tube. There's neon gas and helium gas, and the ratio is about 10 parts helium to 1 part neon. Now, when we put a very high potential between the anode and cathode, which is going to be on the 2 extreme ends of the tube here, that's going to cause the helium atoms to get excited. And when they get excited, they start to move around, and when they do, they tend to bump into the neon atoms. And when they bump into these neon atoms, they actually are able to impart more energy into them than the high voltage potential that's within the tube. And this causes the electrons to jump up multiple states to a much higher energy state. Now, when the neon atoms drop energy states, maybe the electrons are dropping from the 5th shell to the 4th shell, or the 4th shell to the 3rd shell. Or maybe they drop from the 5th shell to the 3rd shell. And whenever they're dropping shells like this, they're emitting photons, and the photons all have different wavelengths. So for example, from the 5th shell to the 4th shell should emit a wavelength around 3.39 micrometers. And when it's dropping from the 4th shell to the 3rd shell, it should be something like 1.15 micrometers. This is in the near infrared range. So when those electrons drop from the 5th shell to the 3rd shell, they emit a photon that is 632.8 nanometers. That's squarely in the red light visible range. So we want these atoms to get excited and then drop energy states. But we want to have some way to, first of all, amplify it so that we have a whole lot of them in a big collimated beam. And we want to ensure that when those neon atoms are dropping energy states, they're dropping the specific amount of energy states that we want to emit this 632.8 nanometer of light. So we create something called an optical amplifier. There are 2 mirrors at the extreme ends of the tube, and then there's a skinny tube right down the center that is essentially creating an optical path directly between these 2 tiny mirrors. One of these mirrors is extremely reflective, about 99.9% reflective. The other one is slightly less extremely reflective. It's about 99% flat. And so what's going to happen is photons are going to be bouncing back and forth between these mirrors. And those photons are going to be in the 632.8 nanometer range. If a neon atom is excited and has an electron in that 5th shell, whenever it is struck by a photon, it will drop the correct number of shells to emit another photon that is of the same wavelength as the photon that struck it. So by creating a very small cavity that is filled with photons of the same wavelength that we want, they're striking excited neon atoms and causing those atoms to emit more photons of the same wavelength. And we end up with this cascading back and forth between the two mirrors of photons causing more photons of the same wavelength to be generated, and we create an optical amplifier. Now those two mirrors, as I said, one was about 99.9% reflective and the other one was 99% reflective. That 1% of light that passes through the mirror is our collimated laser beam that in this application hits a bunch of mirrors and gets up to the moving mirror to create a sweeping pattern to read the barcode. Or in the case of the BOMIM, it goes through the entire optical path and becomes our yardstick so we know how fast and where the moving mirror in the tube is at. Really fascinating technology, but also it's not quite as simple as I just made it sound because, for example, the two mirrors at the extreme ends of the laser have to be extremely precisely placed. And the BOMIM actually plays with this a little bit. They wrap a heater around the glass tube and they can change the length of the tube by warming or cooling the glass, which moves those mirrors closer or farther apart and changes the interference patterns within the helium neon. It's absolutely insane and totally not necessary for a barcode reader here. So how do we use this insane collection of stuff to actually read a barcode? It all starts with the laser tube right here in the center, and interestingly, it's outputting the laser in the opposite direction you would think. The laser is actually pointed backwards towards you. But it hits a collection of mirrors right here on the end that reflect it up and send it out this little window right here at the top. The laser beam flies right past the front of the gun and strikes the barcode to be scanned here. Now here's where the real magic happens, because white reflects light rather well and black absorbs light rather well. So if the pinpoint of light from our laser is striking a dark spot on the barcode here, nothing gets reflected back and nothing gets detected. But if it's striking a light colored spot, the laser light is then reflected back and detected by these little photodiodes on the front. Now there's a little focusing lens here that slides right in to help focus that light correctly onto those photodiodes, and there's that helium neon filter that filters out anything that isn't helium neon light. And this is why we need a helium neon laser, because the pinpoint of light that is striking the barcode has to be smaller than the width of one of the bars. Otherwise the light will spill over across multiple bars, and what the photodiodes are detecting is going to be this weird muddy halfway in between collection of half reflected, half absorbed light. So if it is smaller, then we can very clearly tell if we're on a light bar or a dark bar. But that's only one bar. We've got to detect the entire barcode. So we need some way to sweep that beam across the entire width. And that's what the moving mirror on the top is for. The laser beam is reflected across that, and that wobbles back and forth, which causes the beam to move left and right across the entire barcode. And while that's happening, the photodiodes are detecting what's being reflected, what is being absorbed, sends it through a huge amplifier chain, and spits out a beautiful little square wave out the plug that is a perfect representation of the barcode that is printed on the bottom. This is a really elegant design. I think it's a beautiful piece of engineering, but as you may have correctly surmised, we're missing something. We don't have the computer that this ray gun would plug into that would be able to decipher what that square wave means. And this now raises the next question: even if we did have that computer, how would it be able to decode this? Because the whole variable width thing is a nightmare for computers. How do you know if the fat bar is supposed to be a fat bar? Well, the trick here is that we have the start bit and the end bit just after the quiet zones, and this is the same for every single UPC barcode out there. It goes from dark to light to dark, and it's exactly one module wide for each transition. So all we have to do in the computer is kick off a timer or a counter of some kind that counts the number of clock cycles it takes to make those transitions from dark to light to dark. And then we can use that math as it scans across the entire barcode to figure out exactly how many modules are composing one digit. This is brilliant because it solves the distance problem. If I'm scanning a barcode, maybe I'm holding it here and I've got the ray gun in my right hand. The distance between the ray gun and the barcode is going to vary pretty dramatically throughout the day as I'm doing this. And so if the barcode is closer to the scanner, the bars are going to seem comparatively huge. And if it's farther away, they're going to seem comparatively tiny. But if you have a timer and you have a known reference point, you just update your reference and it just solves itself. This becomes pretty trivial. I'm a bad programmer, so it's not trivial for me, but for a good programmer, this becomes pretty trivial programming. And actually, it was so easy that it was often put onto something like an 8051 microcontroller with very limited space. It's such a brilliant, elegant design. By having the laser reflect off of this, we can very clearly see what is light and dark, and all you need is one tone. All you need is black toner to print out a barcode. You don't need anything specific to go with that. By having the bars be very tall, the beam really only needs the width of the beam itself, but because it's tall, you can be at an angle, you can have a damaged part of the barcode. It doesn't matter. It's what a beautiful design this thing is. Diving into this rabbit hole has been an absolute pleasure. But there is one thing that I haven't done, and I've never put power into this thing. So, well, I think it's time to put 12 volts into it and see what goes up in smoke. And this is what I've got set up to do that. The 9-pin connector that comes out of the ray gun is actually just like a standard DE9. Pin 1 of that is start of scan. This is an output that should tell us when the mirror is moving left to right. I've got that set up on a little jumper here so I can hook the scope up to it. Pin 2 is our digitized bar pattern. This should be what the photo sensors are detecting on the front, turned into a nice square wave. And I've got that on a little jumper here as well for the scope. Pin 3 is an LED. This is just an extra signal from the computer to light up the LED to tell us that we've scanned. Pin 4 is a motor fail. So this is an output from the gun to the computer to let it know that something has gone wrong. Pin 5 is the trigger, which is an output from the gun into the computer. It tells the computer that the trigger has been told, and then the computer sends a enable signal over pin 6. I've just got a little toggle switch here for our enable, so that way I don't have to worry about the trigger. This is effectively our new trigger. Pin 7 and 8 are ground, and then pin 9 is also our 12 volt supply. So here we go. Will the laser turn on? I'll bring up 12 volt supply first, and I'm not expecting the laser to turn on for that because I currently have the enable switched off. So let's switch the enable on, and yes! Oh, that's awesome. The laser did in fact come on, and our little scan mirror is wibble wobbling away, creating a nice scan line. That is way too cool. Well, the laser's healthy, so let's see if the rest of the electronics are healthy, because we absolutely could have a bad op amp in there somewhere. So let's flip the power switch on and see if the scope is putting out any signals here. No, I was kind of hoping to see a square wave on one of these telling us start of scan, but well, you can see that the laser is definitely lasing, the mirror is definitely mirroring, but we're not getting any square waves out of it. I think maybe we're partially functional. If I flip it on here, yeah, check that out. You can see that on the green trace, even though it's not triggering hardly at all because it is disgusting looking, we can see something that does look kind of like a square wave. I think this is going to be our start of scan signal. And then if I move a barcode into here, you can see that we actually get something that looks like data showing up on the yellow trace. Now the voltage levels of this are ridiculously low. We're talking like 0 to 0.2 volts or something like that. If I take a single shot of this, we can see that it very much so looks like we have a start of scan signal and a digitized bar pattern trying to make it out. And I should have thought of this earlier. I'm betting that the two outputs coming out of the ray gun here are actually open collectors. So they're going to need little pull-ups to plus 12 volts to actually pull them up to a positive voltage. So I'm just going to put two little 1K ohm resistors here that are just going to pull those signals right up to plus 12 volts. And here we go, power coming up. Oh, something has definitely happened here. Let's get that guy on there. Let's rechange our scales here to something that makes a little more sense. That is looking way more promising. That's super cool. All right, after a little tweaking, our start of signal pulse here still doesn't look great. I'm only getting about 2 volts change on it, and it's still hyper noisy, but our digitized bar pattern signal here looks awesome. So let's see if we can get in much closer on that and try to make some sense of it. All right, check this out. On the yellow trace here, a high voltage level is going to be a light color, a low voltage level is going to be a dark color. So we start with a light color, that's going to be our quiet zone here, and then we go dark, light, dark. Then we have a wide light, a wide dark, a skinny light, a wide dark, a skinny light, a skinny dark, a very wide light, a skinny dark, a skinny light, a moderately wide dark, and then we're off the screen again. But look at that. That square wave right there correlates perfectly with the first few blocks that we're seeing on our barcode here. So we just scanned this mechanic soap barcode and got the correct digitized bar pattern out on the scope here. How cool is that? Oh, that's so cool. We just scanned a barcode using a near 40-year-old handheld barcode scanner, and we were able to confirm on the scope here that it all came out looking perfect. I went through and compared all of the wibble wobbles on the scope to this barcode right here that came off of my brother's mechanic soap, and they all match up. Everything matches up perfectly. How cool is that? I got to play around with one of the coolest devices I've had in a while. This ray gun makes me feel like an absolute sci-fi hero. It is so cool. So I want to thank you guys so much for hanging out with me today. I had an absolute blast learning about the history of barcodes and barcode scanners, as well as learning about the physics of a helium neon laser. Mike, thank you so much for taking my phone call and talking to me for 2 hours about how helium neons work. It was just fascinating. So don't forget to check out my brother's shop, Love It Sundries. He's an absolute legend for letting me use his soaps here for this video today. And well, I hope to see you guys in the next video.